The maintenance of a fighting force at sea or in the field depends today, as it did 1,000 years ago, upon getting the right thing to the right place at the right time. The basic concepts of logistic support have changed little over the years, only the manner in which deliveries are made. Today, the helicopter has become the fleet's grocery wagon, aerial ambulance, and taxicab. Where early helicopters could scarcely lift their own weight, the helos of today's Navy shuttle loads of 5,000 pounds from ship to ship with ease and in unbelievably short times. This film will cover the duties of the landing signalman enlisted, LSE, and detail the hand signals and safety procedures to be used during helo takeoffs and landings, vertical replenishment operations, personnel transfers, medical evacuations, and helo refueling at sea. The film will present, in addition, an appreciation of the pilot's problems and hazards to the helicopter during these operations from the cockpit point of view. As in every other Navy activity, there are certain rules and procedures to be followed for safe and efficient helicopter operations. These rules are spelled out in Naval Warfare publication NWP 42, Shipboard Helicopter Operating Procedures. Individual aircraft operating limitations are outlined in the NATOPS manuals for each model of aircraft. Among the items covered in NWP 42 are a standardized set of NATO-approved hand signals for helicopter operations, cargo spotting directions, duties of the landing signalman enlisted, LSE, safety precautions, and prescribed clothing colors for assigned personnel. Other important helicopter operation information is also included. The instructions contained in these manuals grew out of the hard-won experience gained during the years that dawn-to-dusk helicopter operations have become routine with the fleet. One very important mission for a fleet helicopter is vertical replenishment of ships at sea. Vert-Rep is the primary method of transferring materiel from combat supply ships to receiving ships at sea. Helicopters can do the whole replenishment job with one obvious exception: bulk fuel transfer. Cargo being readied for Vert-Rep is positioned on the flight deck according to a cargo spotting plan. The painted white lines indicate hover area periphery. These lines are positioned carefully for each type of vessel, so that loads deposited within these lines can be safely picked up by the helo. A clear open deck area must be maintained at all times within the pickup area to allow for a landing after Vert-Rep commences. Vertical replenishment is not a casual operation. It is not a one-man job. It requires extremely close coordination between the helicopter's crew and the ship's personnel. During a delivery, it is obvious that the pilot and the helicopter crew cannot be all-seeing and all-knowing. Because of the built-in blind spots in the helicopter, they must rely upon an outside source of information for critical hover and unloading directions. This source is the Shipboard Landing Signalman Enlisted, or LSE. The receiving ship, therefore, plays an important part in the hover and drop operation by providing this man, this LSE, who must be equipped and trained and be stationed in a conspicuous spot by the drop area. For quick recognition, LSEs must wear yellow, either a yellow jersey or vest, and a yellow flight deck helmet for eye, ear, and skull protection. In addition, all LSEs must wear flotation gear. The recommended gear is the Mark I light vest. If this is not available, the standard shipboard inflatable life preserver may be used. There should be an assigned talker close by but out of the way to provide the LSE with a line of communication to his ship's bridge. The LSE's hand signals must not conflict with the maneuvering of the ship. To prevent foreign object damage, bits of rubbish and trash must be removed from the topside areas prior to the helicopter's arrival. All loose gear must be removed or lashed down. All of these things can become deadly missiles when a helo is hovering close overhead. Eye protectors are recommended for all hands on deck during helicopter operations. When the vert rep helo is on approach, the LSE takes his position. It is his job to assist the pilot by use of prescribed hand signals, guiding the helo into a safe hover position over the ship, maintaining the hover, and warning him of impending hazards. Load handlers wearing proper gear wait nearby, but well clear of the drop area. Any excess people standing around the drop area are not only confusing to the pilot, but dangerous to themselves. Before proceeding, let us take a look at some of the basic NATO-approved helicopter handling signals. Those being demonstrated are not necessarily utilized in the order shown, but are probably used on routine approaches. The LSE, clad in the recommended gear, stands facing the approaching helicopter. Each signal is made distinctly and deliberately. The first signal is this way, or come this way. Then, come ahead. After each signal, the arms are returned to the hover position to indicate completion of the maneuver. Move downward. Move upward. Move to the right. Move to the left. Turn to right. Turn to left. Hook up load. Release load. Wave off. Land. Take off, either to the left or right, depending on the operational plan. Since the pilot in control of the helicopter can see through an arc of only 130 degrees on his side, let's look at a vert rep from his point of view to gain an appreciation of his many problems and how best he can be helped during the brief time he's hovering over your ship. The LSE continuously signals the pilot of the helo's position on the approach and during the hover over the drop area. In the cockpit, the co-pilot acts as a second source of information. At the same time, the air crewmen are watching from vantage points in the helo. They check the load position and keep an eye on potential obstructions. They continually relay this information to the pilot through the intercom. The LSE must advise the pilot, as he sees it, on the status of the load. Guided by all this information, the pilot has a good idea of the position of the load in relation to the ship's deck. He alone cannot always see whether ship's personnel are directly under the load or whether the tips of one of his rotors are too close to the ship's rigging. If the rotor tips, traveling at nearly the speed of sound, should hit something, they would shatter into fragments of shrapnel. Persons have been killed by this fast-traveling debris as far as 600 feet from the accident. The pilot maintains his hover primarily by using some fixed point on the ship as a reference. This will help him to determine not only where the helicopter is positioned over the ship, but how high it must be on subsequent approaches. Since the helo is carrying a load 30 feet or more underneath its belly, this last consideration, height, is a vital one. Maintaining the hover and placement of the cargo are difficult operations. The rolling and pitching of the receiving ship add to this difficulty. It is here, during these few critical moments, that a well-trained, dependable LSE proves his worth as a member of the VERT-REP team. Speed in handling and removing cargo from the drop area is essential in VERT-REP operations. Deck space must be cleared in order that VERT-REP deliveries from the combat supply ships will not pile up. On the fantail of a ship the size of a destroyer, there is little room for the helo to drop its next load. At the same time, pallets, nets, and cargo pendants from the delivered loads must be cleared from the drop area and prepared for retrograde to the AFS. Cargo handlers must remain clear of the drop area while the helo is in the vicinity of their ship. Therefore, they can work only during those short times when the helo is traveling to and from the supply ship. It cannot be emphasized too strongly that a helicopter operation is not an occasion for sightseeing or picture taking. Stay off the drop area and below deck, unless your duty assignment requires you to be there. In order to maintain uninterrupted helicopter utilization during ASW or combat search and rescue operations, some ships are rigged to refuel helicopters in flight. During special operations like this, a few additional NATO-approved hand signals are used by the helicopter crewman and the paddleman on deck. For clarity of demonstration, the paddleman and the air crewman, normally standing in the helo door, will be shown apart from their busy environments. In order to indicate the need for in-flight refueling, the first signal is made by the air crewman. I desire a HIFR. Next, commence fueling. The paddleman on deck signals, am pumping fuel. The air crewman requests that pumping stop. Cease fueling. The paddleman acknowledges. Have ceased pumping fuel. The helicopter requests, desire to move over deck and return hose. The refueling operation is a delicate and precise one, demanding close coordination between the helo pilot, the LSE, and the ship's command and refueling personnel. The latest doctrine and training for HIFR states All men tending refueling hoses must wear flight deck helmets with sound attenuators and eye protection. If one member of the refueling crew is not wearing a grounding glove, let the hoisting cable touch the deck, but do not secure the cable to the ship. A sample bottle of fuel, which will be provided from the ship's tanks, is sent up to the helicopter for inspection. The air crewman has the authority to turn down a fuel replenishment if he feels that the sample does not meet the proper standards of cleanliness and clarity. After the air crewman approves the sample, preparations continue for the fuel transfer. The LSE must know all of the prescribed helo hand signals, make them deliberately, distinctly, and use them intelligently. The LSE must not step over or stand outboard of the refueling hose, as opposed to what we see here. One snap, and he'd be over the side. The LSE must always attempt to maintain eye-to-eye contact with the pilot. The use of correct, decisive hand signals will make the operation a smooth and efficient one. When air transferring individuals from ship to ship or ship to shore, passengers must be carefully briefed on transfer procedures before the helicopter arrives. If landing on board is not possible, personnel transfers are made by hoisting or lowering the passenger with a sling or horse collar. On board ship, 2 deckhands properly equipped with protective gear should be assigned. One to control and ground the cable, and one to support the passenger, who should be wearing a hard hat with eye and hearing protection. Having donned an inflatable life jacket and placed the sling over his shoulders, the passenger positions the sling comfortably under his armpits. He firmly grasps it by crossing his arms around it. He must not grasp the cable. He does not try to help himself until he is completely inside the helicopter. When a passenger is to be transferred from a helo to a ship which does not have a flight deck, the helo crewman will assist him in donning the sling over his inflatable life jacket and position him in the door for lowering. Again, only those whose duty assignments require them to be there should be present in the delivery area. Besides the LSE, 2 deckhands should be assigned, one to control the cable and one to support the passenger and prevent his injury while he is helped out of the sling and life vest. The medical evacuation of sick or injured personnel calls into use a Stokes litter, here rigged with a shipboard litter lifting harness and adequate flotation equipment. The helicopter may provide its own litter and harness, 4 straps of unequal length connected to a single hoisting ring. The 2 short straps are always secured to the head of the litter and the 2 longer ones at the foot. This will permit the patient to be hoisted with his feet tilted downward at about a 30-degree angle. A light handling line is used to steady the litter and keep it aligned parallel to the helicopter's fuselage. Throughout this film, we have seen the LSE performing his role in a variety of helicopter operations, situations which he can expect to encounter many times in the course of his sea duty. As a reminder, let us review some of the more commonly used hand signals, signals that pilots sometimes find difficult to interpret when inexpertly done. The first signal is this way. Move ahead. Hover. Move downward. Move upward. Move to right. Move to left. Turn to right. And turn to left. Hook up load. Release load. Land. Take off. To the left. And take off to the right. Wave off is one of the two mandatory signals the pilot must obey. Stop is the other mandatory signal. It is generally used when the helo is moving on deck. Vertical replenishment, personnel transfers, in-flight refueling, and medical evacuation are complex, fast-moving operations. They are completely dependent upon the close coordination of all persons concerned. The pilot, the air crewman, the LSE, and the ship's command. These men share a common responsibility for the successful transfer of men and materiel by helicopter.
Within the aviation community, the subject of post-crash fire has received a great deal of attention during the past few years. There have been many approaches at trying to reduce the fire threat. The presence of many ignition sources, coupled with the variety of crash conditions, creates a multifaceted problem. But in order for fuel to burn, it must first be spilled. This film is concerned with the R&D programs designed to contain fuel within the fuel system during the extreme environment of an aircraft crash. It has been a program of the U.S. Army Aviation Materiel Laboratories. To better understand the elements involved in fuel containment, let's first look at a simplified aircraft fuel system. It contains two basic components, the fuel tank and the connecting plumbing. Failure can occur in only a limited number of ways. Metal fittings in the tank can be torn out. The tank can be cut by jagged aircraft structure, or it can be ruptured by compressive loads. The connecting plumbing can fail by cutting or breaking. The hoses can be pulled out of the end fittings, or the end fitting itself can break. The high potential for failure in a crash really dictates the design philosophy for a crash-resistant fuel system. Failure must be designed into the system. It must be made to fail at predetermined points. To determine the common failure points, a series of more than 30 Army-sponsored crash tests spanning more than 9 years was conducted. These dynamic tests of actual aircraft in typical upper limit survivable crash conditions have included both rotary wing and fixed wing aircraft of many types. Here's a good example of a fuel tank attachment which was pulled from a tank. In this case, the filler cap area was ripped from a tank because the cap support was rigidly attached to airframe structure which was displaced. This is a fuel tank which was punctured by floor structure displaced during a rough terrain crash landing. Here, a tank cut by jagged metal continued to rupture under compression during crash impact. Failures of this nature produce a catastrophic spray release of massive quantities of fuel. The liquid in this case is dyed water, not fuel. Failures in the connecting plumbing system can also create fire hazards. Here is a fuel line which has been pulled from its fitting. Another in which the fitting broke. This rigid line was mashed flat and torn in many places. This pattern of failures has been repeated in test after test. Clearly, if a fuel system is to be made crash-worthy, these are the components which must function in the crash environment. Analysis of crash data indicated that crash-worthy fuel tanks must have two basic qualities. They must be cut and tear-resistant. A testing program was initiated to evaluate material specimens which appeared to have the desired qualities. Following this initial program, several experimental fuel tanks were built of the more promising materials, and full-scale crash tests were performed on both fixed and rotary wing aircraft. Let's look first at the fixed wing. The aircraft were accelerated down a monorail to guide them to a precise impact point which would duplicate under controlled conditions the environment of typical fixed-wing crashes. Two experimental fuel tanks were installed in each wing of the test aircraft. The results of this test were extremely encouraging. There was no leakage in the left-hand wing tanks, even though the wing was ripped from the aircraft and preceded the fuselage over the impact barrier. The right inboard tank was torn free from the aircraft by the telephone pole and was thrown clear of the wreckage. Perhaps the most severe impact damage occurred to the right outboard tank. The telephone pole struck the center of the tank, caved the wing in more than halfway, and dramatically rearranged the tank volume. The top and bottom of the wing structure was severely bulged by the tank, but the only tank damage was a slight pinhole, which allowed only minor seepage. But crash resistance in fixed-wing aircraft is only part of the story. Rotary wing aircraft crashes produce far different acceleration forces. Massive vertical loads on helicopter fuel tanks have traditionally produced catastrophic tank failures. This crane drop test is a good example. Both the fuel tank chamber and the bladder tank failed. The crash impact compression force was sufficient to rupture the fuel tank, instantly releasing the entire content. The patterns of water spillage on the ground indicate how extensive the spray of fuel would have been in an actual crash. A similar drop test with a crash-resistant fuel tank was made even more stringent by the attachment of two large rocks to the helicopter structure. This provided the worst type of crash environment simulation, a crash in very rough terrain. In contrast to the previous rapid total loss of fuel, the new tank material showed an ability to survive even the extremely localized impacts produced by the two rocks and the associated jagged metal structure produced by the rock penetrations. The tank sustained only very minor cuts, which failed to propagate due to the new tear-resistant material. Extensive testing was performed using up to 11 different tank materials and configurations in a single helicopter floor area. Standard and self-sealing bladder tanks, aluminum, and several types of the new crash-resistant tanks were evaluated. Testing was even done with the tanks restrained from possible upward deformation by heavy simulated cargo. The results of these tests showed that tank materials were truly crashworthy only when they possessed certain qualities. They must require at least twice as much energy to continue tearing than the bladder tanks in use today. Aluminum tanks, for example, fall well below the desired energy level, even though the force required to start a tear is quite high. Although failure of the tanks is the primary cause for massive release of fuel during a crash, obviously the entire system is potentially hazardous. Good tanks are valueless if fuel pumps or other fittings are torn from the tank, leaving large holes for escape of the fuel. Let's look at the highlights of some of the plumbing system tests performed in the evolution of a complete crash-resistant fuel system. Current metal fittings tear out of the fuel tank at loads which are considerably below the tank wall strength. Several techniques were developed to increase this load. The wedge lock concept shown here provided a retention capability that equaled the strength of the tank material. Tests were made on various tank-to-metal configurations, and in every case, the wedge locks functioned as designed. Failures occurred in the tank material rather than at the wedge lock joint. As stated earlier, for a crash-resistant fuel system to function, failure points must be designed into the system. Provisions to permit the safe separation of fuel lines from crash-displaced tanks and components were considered. Tests were performed on devices which could trigger standard quick disconnect valves. The triggers convert tension, shear, and bending loads into a pure tension load, thus separating the valve at the disconnect point. Testing under impact conditions typical of marginally survivable accidents proved that the valves would function as efficient breakaway valves. A careful evaluation was made considering the many factors involved in breakaway valve separation. These include such aspects as valve closure, triggering, fuel loss, secondary fuel spillage, and inadvertent valve actuation. Among the tested valves, there were many novel approaches and some unique benefits in almost each design. Self-sealing breakaway valves were developed to fit between tanks or to connect tanks to fuel lines. These valves were designed to close and break away when fuel tank displacement occurs. Failure of the frangible sleeve shown here will allow valve closure and separation if tank displacement is great enough. The whole area of frangible materials became an important part of the component test program. In order to design failure into discrete points in any system, materials must be included which will fail at a given point, sooner than the materials which surround it. The evolution of these materials, whether they were fasteners, rings, brackets, or supports, became a painstaking process of test and evaluation. Static tests were performed in both shear and tension modes, followed by dynamic tests, which were designed to simulate as closely as possible the failures anticipated in a crash environment. Every element of a fuel system was tested on a component basis, and the most likely materials adapted toward the design of a prototype crash-resistant fuel system. Successful component tests and dynamic tests on obsolete aircraft were fine to validate theory. But the ultimate measure of a crash-resistant fuel system would have to be made in a currently operational aircraft. Accordingly, the decision was made to test an entire integrated crash-resistant fuel system in a UH-1A helicopter. This turbine-powered helicopter is in the famed Huey series and represents the largest single family of aircraft in the Army aircraft inventory. The aircraft was modified to include the elements of the new fuel system. Both of the standard bladder fuel tanks were removed and replaced with special crash-resistant tanks made of multiply nylon cloth material. Special valve triggering devices were molded into the tank walls during manufacture. Aluminum tank top access covers were replaced with ones made of tank material. The boost pump was mounted on a tank material diaphragm rather than an aluminum one. The aluminum crossover tubes were replaced with ones made of tank material and were attached to the tanks with self-sealing breakaway valves. Rigid fuel lines were replaced with flexible hoses. Quick disconnect valves and trigger mounts were used at all places where the fuel lines attached to the tanks. Frangible attachments were used at the tank filler opening, the boost pump area, and other attachment points. The oil plumbing was redesigned to make it more crashworthy, and the oil reservoir was covered with felt, sealed with a polyurethane coating. Coils were formed in hydraulic lines to permit line extension rather than rupture during the structural displacement of a crash. The electrical system was also modified to eliminate possible ignition sources. In order to achieve the maximum benefit from such an important dynamic test, the helicopter was actually operated on emulsified JP4 rather than conventional liquid jet fuel. This was a slight insurance policy, since should some part of the fuel system fail to function, the emulsion would not spill as readily as liquid. This feature would help to prevent an actual post-crash fire. The helicopter was crashed by means of a radio-controlled flight system in a 12-degree nose-down attitude from a height of 65 feet. After impact, the helicopter slid for 180 feet. At about 90 feet, the helicopter rotor dug into the ground, creating an overturning moment with the result that the aircraft came to rest on its left side. There was no fire on impact, during the slide, or when the helicopter came to rest. There was a slight release of some hydraulic and transmission fluids. Neither spillage proved to be hazardous. All of the elements of the fuel system functioned satisfactorily. No fuel spilled at any time during the crash or during the post-crash investigation. The fuel tanks were not punctured, despite the fact that the bottom corner of the right-hand tank was gouged by supporting structure. The triggering valve mounts were undamaged during the crash. The valves were leak tested for several days, and no seepage could be detected. The wedge lock retention technique performed as designed, securely holding their rigidly attached components throughout the crash and subsequent leak checks. The boost pump mounting diaphragm and the frangible attachment bolts functioned satisfactorily, protecting the pump and the drain from the rock-simulated rough terrain environment. All the flexible fuel lines functioned as anticipated. During the crash, the engine was displaced several feet, causing separation of the quick disconnects at the service deck. The oil system experiments functioned as designed. No oil was spilled. The engine oil reservoir sustained a severe blow which split a seam, and oil was spilled onto the felt, but external leakage was prevented by the polyurethane coating. The transmission was torn free of the airframe basic structure. The main case casting failed at the tie-down point. The flexible oil line placed between the transmission case and the sump was elongated and crushed by the transmission displacement, but did not leak. 7 of the frangible clamps holding down wires broke and permitted the wire bundles to move with the deformed structure rather than remain rigidly attached and be broken. The felt insulation placed around 3 wire bundles shielded the wires from collapsing structure. The one gnawing doubt that plagues researchers in a successful test, such as this one, is that one event does not give any predictable statistical probability. You need at least 2 to start statistics. Consequently, the entire crash-resistant fuel system was reassembled in the center section of the fuselage and dropped from a tower to subject it to an even more stringent crash environment. Parts of the system which were not functioned in the previous test failed safely in this drop test. The only part of the system which did fail was one of the boost pumps which had not been installed with a wedge lock connector. Clearly, to have a functioning system, every element must be carefully redesigned and well fabricated. One of the continuing goals of this Army-sponsored research is the dissemination of the research findings through the aviation community. A good example is the AvLab's Crash Survival Design Guide. Its section on post-crash fire lists many suggested criteria for the design of more crash-worthy fuel systems. Detailed information on the work shown in this film is available in AvLab's Technical Report 68-82. As an adjunct to these publications, supplemental information is periodically issued, such as these curves to figure breakaway loads for fuel fittings. Plots for various hose fitting combinations were evolved on the basis of component test programs. A designer need only select his type of hose installation and read off the value for the fittings. This convenient graph puts the results of hundreds of dynamic tests at the fingertip of any aircraft designer. These favorable prototype test results have led to design and fabrication of production crash-resistant fuel systems. Provisions have been made for the retrofit of aircraft currently in the field. Production line modifications have been made to include this important safety feature in new aircraft as they are being manufactured. This program is being carried out with all the aircraft in the Army inventory. Future Army aircraft will be designed to incorporate on the drawing board the crash-resistant fuel system features. Army thermal fatalities in impact survivable accidents have been significantly high. Reduction of at least 75% is expected when the new fuel system gets in the field. A corresponding reduction will be effected in burn injuries which do not result in fatalities. With Army aircraft utilization rising each year, it is none too soon to provide the measure of personnel safety, which is attainable with a crash-resistant fuel system.